What is the wavelength of this signal? Anybody want to tell me the first step? Megahertz to hertz, okay. So we have our frequency, but we'll put that in a different color. Frequency is 13.5 megahertz. You know, for a problem like this, it doesn't say put it in standard notation, which is like 1 point something times 10 to the something in scientific notation. So you could just leave it as 13.5, and then the mega means what? 10 to the 6. So then that's just because 10 to the 6 hertz, right? And if you get something that you don't, like I don't know what a nano is, so that doesn't make sense. Remember, you have those in your reference table. Okay, so we have our frequency. What equation relates wavelength to frequency? V equals lambda f, right? Oh, but to be able to solve this, we would need what? We need to know what V is. But what did you say? Okay, that's a good. Let's rearrange it too. That makes sense. Like that, right? So the nice thing is, you know, the math in this unit, there's some signs, you know, with the Snell's law. But other than that, there's nothing too complicated. So if you're someone who gets hung up on the math sometimes, that's a bonus. Maybe. Yes. Okay. We're going to make fun of you on the video, so you might want to watch that. I'm just kidding. Huh? Oh, he does, doesn't he? Ellen DeGeneres, right. Especially that sweater. You should put that on and do dance for us. So, that's not a bad person to look like, though. Okay. Now, what, though? We need V here, right? V equals 3 times 10 to the 8 meters per second, right? Okay, so lambda equals 3 times 10 to the 8 meters per second over 13.5 times 10 to the 6. 1 over seconds, that's a hertz. So the 1 over seconds cancel, and you have meters. So 3 e to the 8 divided by 13.5 e to the 6 is 22.2 meters. That's a big wave. That's good because, in fact, if you think of TVs and radios, the large wavelength is what allows them to like go through buildings and stuff and come in, and we can pick them up and get them in cities. Although even in the city, you know, like a radio station before it was HD, would start to go out and stuff. Actually, even the HD radios go out in the city. The signal's having trouble getting in to your receptor on your car. Okay, so that's pretty simple. Here's another one, number 2, about adding some waves together. Let's see, I'm going to get some grid action going here. Let's just okay, I'm doing, hold on. Let me put points on there because it's getting too confusing. Who, me? Just to Toronto. I went to the new science building, or new, I'm sorry, aquarium. It was pretty cool. They don't do a very good job with like any sort of explanation of anything. It's all just thrills. Yeah. I mean, they have little things on the side, but there's not much, you know, they, like their things are feeding. It's like they just show people feeding it. There's no like, discussion of anything. If you go to the Baltimore, you can see like how the sheep. That's a horrible way. What did I do? What did I do wrong? I'm having trouble. Yeah, sure. I would never make fun of Kelly. We'll do one simple here. All right, so there's one wave. Now, wait, the next wave we'll do. That's the same. Quarter. All right, now roll. I think. When some of you added these waves together, um, then yours were like straight lines like that. But if this is curved and flows like a sine wave, right? And this is curved, flows like a sine wave, then the addition of them should be what? Not straight lines going to point. It shouldn't be like this. But what principle do we use to get the sum of these? It's a simple one. Yeah, so it's called the principle of superposition. Okay. So we want to add these two together. But to do that, you got to know your midline. So here's one midline. That one's easy. And then this one's a little more, not too hard, because I have the dots right on it. We could see the midline there. And so if we look at this point here, what's our value? What's our value here? Yeah, 2, I guess. Or let's say 1. And then we'll take the blues as half. So that's minus 1. And then this is what, then? Minus 1.5. So our sum there is minus, 2.5. 0 and 0. 1 and 1.5 is 2.5. So 0, and then we repeat. Okay? So I won't do the whole wave here. But we'll have this as our midline here. And we're 2.5 down. Then we go to 0. Oops. Start it over. 2.5 down. 0. 2.5 up. 0. 2.5 down. Notice that I didn't really take off on your packets if you didn't have it, but it should be smoother. We go up again. Does that make sense? So, of course, I can make them a little harder than that, right? But not make them so in phase. Well, it's the same principle. It's just like you take the midline, and from the midline you have a value up or a value down from where you are. And each of those, and then your other wave, or even in other three waves, you have a midline and you have a value up and a value down at that point, or down. And so then you take whatever that is and add them together. Then you make your, so if your sum goes up and then just comes down a little and goes like that and then goes like that, that's okay. It will come out in your points, right? Numero 3. A ray of light well, who's doing the day of silence? No one? Will's doing it? Now, is that, all right, let's not use the term wife beater for t-shirts. Yeah, I know what it is. A block of diamond at an angle of 45 degrees. What is the angle of fraction? Now, if I say, if it's not, if it doesn't seem clear if it's talking about the incident angle and the refracted angle, just assume that it's the incident angle and the refracted angle. And the incident angle is always to the what? To the normal. So, oh, yes, okay, I see what you're saying, yes. But in the sketch, to the normal. And it's always important to draw a sketch for these, too, because it's going to show you, like, it just makes sense. So what I mean by that is if you have, it says incident upon at 45 degrees, well, in that case, it wouldn't matter. But if it didn't say refracted angle of refraction and just said what does it travel in the diamond at, assume that I want the angle of refraction is what I'm saying there. Okay? Is it going to bend towards or away from the normal? Now, we want to be able to figure this out. Well, corn oil, the N is what? 1.47. And for diamond, N is, okay, so we're going into a higher N. So it's going to slow down. We could think of our wheels, if that helps. When this slows down, what happens to this wheel? It speeds up and keeps going, so it's going to turn that way, because it's going to get, that's going to go faster and cause it to turn. So it's going to bend towards the normal. Now, I might ask you some questions in like the multiple choice where you have to think that through. Right? And if you have trouble thinking it through, well, then draw something like that and give it a thought, okay? And then use your sketch to help your thought, okay? No, I'm just saying. It probably is one. N1 sine theta 1 equals N2 sine theta 2. This is our N1, and that's our N2. So we're coming from corn oil of 1.47 at 45 degrees into diamond. Okay. So if we multiply these two things together and then divide by this, then we'll get what sine theta 2 equals, right? So we'll multiply 1.47 times the sine of 45. Make sure your calculators are in degrees. And then we'll divide that by 2.42. And that gives us 0.43. Make sure you can get to that part if you own one of these things. Was it hard to get up? Were you guys sleeping till like 11 every day? 10? No? You know, Will actually went to bed at 3:30 on Friday afternoon and break, and he just woke up. Hibernated. That's why his hair grew so much. I like it, Will. It looks good. How long are you going to let it grow over the summer? You haven't decided yet. Is that what you guys grow your hair out? I thought you do play hockey. All right, see if you can get to this point. I used to have long hair down to my ankles. I did shave my head once. I had to leave a note on the door for my wife. So I said, don't freak out, but I'm bald. Like, shaved it with shaving cream and stuff. Well, what happened was, I was going into field camp for a number of weeks, so it's going to be out in the, which actually shaving your head before you go into this is not a good idea because it's uncomfortable and you burn and stuff. So anyways, it's going out, so I was going to be away from like showering and stuff for a few weeks. No, there's no, it's like out in the, like out in the mountains, Colorado and stuff, yeah. So, I mean, there's streams and stuff. You clean yourself up. We bring in water to drink. So that was, I tried to shave it like with a shaver, but then that didn't look good, like with one of those things. And then so it ended up bald. Anyways. Yeah, it would be kind of weird. It is a little weird, yeah. So 25.5 degrees. Okay. Good. Everybody got that? 4. What is the critical angle for light? Trying to escape glass. Into water. So we're typical thing. You'd have a block of glass floating in water, right? And a light source coming out of it. That's the water. Now, as it comes out, we're wondering what this angle is right here, because that's the critical angle. We'll call it theta crit, or just theta CR. Yeah, it's sort of the physics gang. What's the angle of refraction at the critical angle? Like that, right? So you see that your angle of refraction goes all the way to 90 degrees for your critical angle. So you start with the Snell's law. And N1 is coming from what? Glass. What is glass? Now glass, I should just say, there's lots of different types of glass with different index of refraction, or indices of refraction. So I'm just giving you an example up there. 1.63. There's crown glass and flint glass, to name a few. And water is what? So that would be our 2, and this one would be our 1. So we have 1.63 sine, our theta 1 is theta crit, is 1.33, but we have the sine of, what's our theta 2? 90 degrees. Now the sine of 90 happens to be what? 1. So 1.33 divided, because this is just 1, divided by 1.63 is 0.816. And then sine inverse is 54.7 degrees. To get into the club, you have to know all the angles, critical angles. Let's do one more that might be helpful for you on your test. Because you have this equation, you have your wave equation. Also remember, frequency is 1 over period. Period is 1 over frequency, right? But also remember N equals C over V, right? Okay, because that's one we only did a few problems with. And the problem that we'll do that is the speed of light in an unknown material is 2.2 times 10 to the 8 meters per second. What is the index of refraction? For the material. Well, as long as you have the equation, and as long as you know what C is, then the index of refraction is just a ratio of the speed of light in a vacuum to the speed of light in the material. And N, what's the speed of light in a vacuum? C? Oh, I want to mention one more thing. Don't let me forget. The 10 to the 8s just cancel away, as do the meters per second. So we have 3 divided by 2.2, or 1.36. it must be acetone. Okay, acetone or isopropyl alcohol. Oh, the other equation that you should remember is this one. No, unless I ask, like, what is the likely? Yeah, you look at your table. This formula here, right, way back from the beginning of the year and throughout, it's just our speed formula. But remember, you're not always given, like, the wavelength as your distance and the frequency as the reverse of your time. So you have to look at that because sometimes you'll be given one and says, like, a sound wave, 330 meters per second, right, travels is heard by a person who is 50 meters away. How much time does it take to get there? That's this equation, isn't it? Right? So remember that there's this one and this one. This is for when specifically you have wavelength and frequency. But you might be given distances and times that aren't periods or wavelengths and stuff. And in that case, you're using this one. Like a common example would be an echo, right? Like Little Bear talking to the moon, right? That's from a children's book. Little Bear talks to the moon. It's the moon's birthday as well as Little Bear's birthday. And he buys the moon a hat. And then the hat blows away and ends up in a tree, and so he thinks the moon bought him a hat too. Okay. That's it.